I am trying to give you an idea of a new concept, and my objectives are to sell you, to be like a real salesman, to sell you not only the idea, but also the way how we can apply this, especially for our future eRHIC, electron-ion collider. What do we want to do? We want to, if possible, reduce the size of the accelerator or the magnets themselves with ability to allow them to accept a very large energy range, but in a small pipe, which is a little bit controversial in the sense of the accelerators, because when you look at the present accelerators, they're all synchrotrons. They have a very small pipe, and the beam is very much contained in the small pipe, but contained by changing the magnetic field. What happened actually is the muon collider collaboration group was confronted with the problem of accelerating very fast decaying particles, muons. Fast. But it's not possible with the synchrotrons because they would basically decay. So we were looking for the solution, and one of them is, of course, linear accelerator, but very expensive. So it's always the same problem, reduce the size. So I'm now giving you major points of my talk for the eRHIC here. We would like to reduce the cost of the eRHIC. Presently, we have in the present design 2 Linacs with 2.4 gigaelectron volts. To reduce these two to 1.9 gigavolts, 900 megawatts. And then we would like to reduce the size of the injector, and instead of using 6 arcs, we would like to use only 1 by using this simple method of the focusing many energies into one pipe. Why 6 rings? Because you cannot put different energies if you use the synchrotron into one ring. The moment the energy changes, which is in the nanosecond region, you cannot ramp the magnet so fast. So you have to have 6 rings to accommodate for 6 different energies. I'm going to beat this up. I'm going to put 1 pipe and put all the energies into 1 pipe, which will be no different than the one more or less present. The other subject I would like to show you today is, I hope you can see the man here. This is the gantry in Heidelberg built for the heavy ion beam of carbon ions. This gantry, which treats the patients already a couple of years, is built with such a large size because the magnets are warm and large, because the energy of the carbon is very large. So what I would like to do is to replace 130-ton weight of these magnets with magnets built at BNL. I would like to use this type of magnet, superconducting, where all the energies of the treatment will go through the same pipe. So these are basically the points of my talk. But now I'm going to show you a little bit of history to connect all these kinds of accelerators. How did I come up to this idea? And how this can be applied in these cases. Then I will go a little bit more detail into the eRHIC applications, how this is going to work, and I will show you details of the medical applications. If I have time, I can show other possibilities, because we have a very active group here with Francois working on the accelerator-driven systems. So there are very good ideas how to use the same kind of idea of the smaller size but still able to drive the reactors. So what are the accelerators? As Phil said, my first accelerator was 150 kilovolts. That's basically, you can take the batteries, pile them up, and make this voltage accelerate particles. I did accelerate heavy ions, produced infrared diode twice more sensitive than anything on the market at the time with antimonum ions. But what is the accelerator? It has always an ion source, probably some plasma, dual plasmatron ion source or magnetron, where from the plasma you have to extract the ions, missing electrons, with some electrostatic potential to get it out and direct to the targets. So I will skip the electrostatic accelerators. They are in the 1870s, started with Van de Graaff, with Cocker-Walton, and so on. I will start with Linux. It was a fantastic idea what they come up with, because as you extract these ions from the ion source, they gain the energy because of the potentials, positively attracted by the negative electrodes. So they synchronize the motion. As the particle gets between these gaps, an energy gain because of the differential in voltage, they get faster. And as they get faster, they pass longer path. So that's why these drift tubes are longer and longer, because the particles are becoming faster and faster. But you have to synchronize the electrostatic potential in such a way that when the particles arrives to the next position, it gets appropriate voltage on these electrodes. So it's oscillating field, and in this case, this is non-relativistic particle. It gets accelerated through the structure. Alvarez-Linac is one of the known things. So when I was at a lecture of the Accelerator Physics School, I confronted Bob Palmer, who was giving a lecture of those Linux. He said, well, that's nonsense. We don't need these long Linux. We can take the Linux, put 4 rods, bend them around, and switch the phase next turn, and it should work very well. So he stopped the lecture. We like 30 minutes. We said, how can that work? At the end, we figured out it would not work because the electrostatic forces were not strong enough to keep as the energy goes up. But this is the same problem Lorentz was confronted with. So how do I, instead of having this long Linac, get all this in the small space, accelerate the particles by using these orbits, putting them into the magnetic field. And on the top of these 2 electrodes, as the particle goes from the ion source here and gets accelerated by this potential difference between these electrodes, they are also oscillating. So as the particle gets accelerated, it gets bent by this magnetic field where this is put in by the Ds. So it is very trivial cyclotron resonance to compensate the force of the centripetal to the centrifugal force, which is a Lorentz force, speed by the field, and centripetal force when you drive a car on the big curve, you would be pushed to the right side if you're turning left. So these 2 forces are compensated, and the voltage is also synchronous to the motion, so it works well. It works so well that for this device, they got the Nobel Prize. He was very lucky to have a very good graduate student who was able to make it work. Basically, he moved to the Brookhaven lab later on. As you accelerate these particles faster and faster, and they gain energy more and more, the problem becomes evident with the focusing of these particles on the sides. That was okay for a while, reaching, according to Bethe, these were not possible to go above 1 GeV. they stopped working on it for a while, but now the problem is how to make this focusing to work. So it was clear that you have to introduce some alternating forces to keep these particles contained as you reach to the higher and higher energies. So that's how they came up to the concept of the fixed field alternating gradient magnets. The focusing is produced by opposite magnetic field. So the two magnets bend a regular way, while the medium magnet is bending opposite way. All the orbits of the particles as they go from the lower to the higher energy are parallel to each other. And this was derived by, independently by 5 people. One is in Japan, Yukawa, one is in Russia, always something in Russia, Kolomensky, and Simon and his co-authors, Kirst, derived this in Wisconsin. It's a beautiful machine in one sense because everything is more or less perfect. There is no chromaticity. Chromaticity is dependent on the momentum. I don't want to bother you about these other details, but all the orbits are very much parallel to each other. They even designed a collider in this case to collide these particles. But the problem was this enormous magnet, which has to contain these particles. The orbit offsets of these particles were of the order 1 meter. At the time, again at Brookhaven National Lab, Courant, Snyder, and Livingston came up with the concept of the strong focusing synchrotrons. And that killed basically the fixed field alternating gradient machines because they have much smaller magnet. So basically, this is today, all around the world, accelerators are strong focusing synchrotrons, not radial FFAGs. We have now at eRHIC 3 of them, booster, AGS. This is the first synchrotron, AGS. They're alternating focusing between magnets, transversely focusing, vertically focusing, transversely focusing, alternating around and keeping the particles very much contained in the small pipe. And of course, we have eRHIC, where we have 2 superconducting rings, yellow and blue, where the particles are again kept in the small pipe. So what kind of accelerators we have? 3 types. You heard about the cyclotrons, where the field is fixed and the frequency is fixed. So as the particle goes around, it gets to the higher and higher orbits. It's not relativistic yet. As it reaches the relativistic case, it's a problem because there is no more way to control, to produce that strong field. So one of the present cyclotrons at Paul Scherrer Institute in Switzerland is still beating the $2 billion project at Oak Ridge. They are still beating them badly. They are still way behind. Because it's a fixed field, it's a relatively small machine, and the space charge is also okay. What are the synchrotrons? Synchrotrons are drawn schematically here with much smaller magnets than the fixed field accelerators. But the magnetic field has to follow the frequency of the RF synchronously. So it has to be as fast as possible, but reaching the limits of the order of 60 hertz, 100 hertz today, very difficult to make it faster. And that's a problem in many applications. In the case of the radial alternating gradient FFAGs, fixed field alternating gradient, the magnetic field is fixed. So you don't need to change it with the frequency. Frequency is changing, but the problem is as you accelerate, the momentum is changing, and it has to follow, the radius has to follow the momentum. by this law. So the field in a magnet is not, it is fixed, but it is changing very fast. And when you get to the higher energies, it has to go very much up high, which is a problem. So what is the focusing of the particles? What is containing these particles together is the transverse force. There are three cases. In this case, it's the bowling alley, where the ball will not be, it's neutral here. You don't know where it's going to go. In this case, it's not stable. But if you keep the forces active on the particles on both sides, it's going to be stable. So this is basically the alternating focusing, where we have focusing and defocusing magnets in series, keeping the particles in the small space. This is a schematic of the basic cell all around the world. All the synchrotrons have the focusing and defocusing magnets. Between these quadrupoles are the bending elements, and that's why the new definition of the dispersion comes from this bending. These beta X and beta Y are actually amplitude functions of this beam inside of the pipe. So when you put the quadrupole inside, it would act on the beam transversely. In one case will be defocusing. In this case, in the horizontal plane will be defocusing, while in the vertical plane will be focusing, depending on the direction of the beam. So this is very critical parameter I will be discussing very soon, this dispersion function. And this is basically our accelerator, relativistic heavy ion collider, eRHIC, where alternating focusing is all the time present along the arcs. The other machine I'm mentioning, the fixed field alternating gradient, were built again in 2000. This is a revision from the area in the 50s. So they started to get built in Japan, and they basically had a proof of principle for protons to accelerate the particles where lower energies are oscillating. There are three magnets in one block, oscillating around, gaining at higher and higher energies as they go, as I show that in this picture. In the next accelerators, there are two of them of the same type. One is at KK, now it's moved to Kyushu University, and the other is at Kyoto University in Japan. Is driving the reactor with a very small currents. They're just doing experiments of the cross sections. So what happens here is from the ion source, it's getting ejected, particles are oscillating, and presented here you have three magnets. The central magnet is bending opposite way, and all the orbits are moving radially out. So what do I want to do? My major idea is to combine now these two kinds of accelerators. One is the radial fixed field alternating gradient, which does have all the momentum in the same pipe. And the other one is the synchrotron, which has all the particles also in the same pipe, but you have to change the field. So I'd like to keep the field unchanged and accelerate the particles in the same pipe, replacing this big magnet with a small magnet, if possible. So where is the logic here? The logic comes from this basic relationship between the orbit offsets of these particles in the machine, the momentum, the energy which we want to keep the particles inside, are connected by the dispersion function. So if I can reduce this dispersion function, I can have this delta x very small for the large momentum. So what is the dispersion function? If you put the two energies into one bending magnet, as they come out, they will come out at a different exit, because one has higher energies, bend less. So the dispersion definition is this delta x divided by the difference in momentum. That's the definition of the dispersion function. So it is connected to the bending field. Happened to be that around the time when we were confronted with the muon accelerator problem, how to accelerate muons fast, that I worked at the time on improving the UV lattice of the synchrotron light source. And what is a synchrotron light source? These are electrons oscillating in the synchrotron at the end of the bending elements. The light, synchrotron light, gets emitted always in the direction of the motion of these electrons. So you would like to have as small beam as possible, as smaller emittance of the beam as possible to get the better synchrotron radiation focused to the targets. And the basic cell of these elements has the bending element as a defocusing, usually combined functional magnet. Sometimes it's not combined, but basically there are two elements laid out in this case: focusing, defocusing, and two quadrupoles. And this is the thing I have been working on together with Ernest. We published some papers deriving how to improve this as much as possible. And it occurred to me that, I already have in this case this small dispersion function. The largest value is 0.3 meters in the light source lattice. And to have that done, I have to make some conditions. Don't want to bother you much. The minimum of this radial function should be in the middle of this magnet. Minimum of the dispersion function should be in the middle of this magnet. You put all these things together. It has to be length of this magnet has to be this much. Pentatron function has to be this much. And then you get the smallest possible emittance, the smallest possible dispersion function. And it happened to be that, again, at BNL, Green and Chasman came to this concept of the smallest h function, where this dispersion function minimum is achieved by this combination of magnets. So now I'll go back to the alternating gradient synchrotron. And we have, in this case, opposite condition where the focusing is in the middle, while defocusing is on the sides. As I showed you in the light source, it's opposite request, that the defocusing is in the middle, on the sides are the focusing. By the way, they accepted now even in the scaling machines this concept, so they are changing now in the scaling machines in Japan, even in England. They are putting now finally on my persistence, the defocusing in the middle to reduce this size of the magnets to half. But that's not what I want to do. I want to have the pipe no larger than 8 centimeters, let's say. It can be even smaller. To have the pipe of 4 centimeters, I have to have the dispersion of 8 centimeters. As you saw before, in the light source, it was 30 centimeters, still a little bit off, but not much. So I'd like to now reduce this size of the magnet to this, to get 3 centimeters. In addition, I would like to put a very much linear field in this machine. Linear field means no problems with the stability of the particles. Everything is, a dynamical aperture is basically infinite if you don't have very, you don't have nonlinearities. So this was the first design we have done for the muon acceleration, where you have 3 elements. There was necessary room between them for the cavities to accelerate these particles fast. So the magnets are very small. That means that the focusing of these particles is very strong. It's like much stronger than in a synchrotron because the size of the focusing is defined basically by the size of the magnets. The orbit offsets were of the order of 50-30 millimeters, and there are a lot of other properties which abandon the scaling laws which are in the radial machines. But it works. So it works so well that they build it, actually. They build it in England on the idea that to make a proof of principle, does this really work? So they made these small magnets. You see how small they are? Tie them up together, and there are some properties expected from this machine that as you change the energy, the cell tune, which is variation of the oscillations along the orbit, has been predicted to be the dotted line. The dots are the measured values. The orbit offsets are of the order of plus minus 9 millimeters, which is very small. The pipe is very small, and it confirmed the predictions. And as you accelerate these particles around, they are already relativistic, there is a path length difference, which is supposed to be parabolic function, and it was shown to be. So now I'm going to use this example and apply it to the existing eRHIC design. We already got the support from BNL. We were able to hire probably the most talented guy in this field today on that LDRD. He's actually starting to work tomorrow. We would like to reduce the cost of the eRHIC because it happened to be that all these 6 rings with all magnets, power supplies, cables, long Linux were way over the value which would DOE approve. So we would like to reduce the cost. In the first stage, we would like to go all the way up to 10 GeV. 12 GeV is the energy of the Jefferson Lab Linux. We can even get 12 if we want with the present design. And we would like to put everything in the eRHIC tunnel. So we don't want to have any civil construction, which is usually costly. So the 6 rings we would like to replace with 1. Permanent magnets we would like to use, not the power supplies. But we would have some correction coils in the case of the errors. We'd like to reduce the Linux size from 2.4 to 0.9 GeV, having more passes through the Linux. And we would like to replace the injector from 600 to 100. But why eRHIC? I had to borrow some transparencies from Elke Aschenauer. Why do we need this machine? Well, there are many physics questions we need to answer. One of them is the proton spin puzzle. Where is this spin coming from? Gluons, and how do they contribute to the spin of the protons? We would like also to make a microscope into the basic forces between the nuclei and partons, as well as in the ion collisions, electron-ion collisions. We would like to see where is this critical transition point. So we had the design of the eRHIC, which happened to be too expensive. We had a lot of rings for different energies line up above each other. We had 2 Linux. We had the injector. This is the cross-section of the Linux. So right now, I'm starting with the existing eRHIC tunnel, which has 2 superconducting rings. I'm going to put a Linux of 900 presented here. Then connected to the injector of 100 megavolts. Have a loop in the tunnel because the energy is only 1 GeV to get energy up to 1.9 GeV, and put the FFAG ring now around. So I schematically showing these magnets which are only 6 centimeters wide. Either we don't know exactly where they're going to go, but they are very small. And I will go through this LINAC 10 times from 1.9 GeV to 10 GeV. How does this happen? How can I keep these particles in the small pipe? Well, under these conditions, as I showed you before, I have only 2 magnets this time, where the orbits are shown here. So the 10 GeV orbit is 10 millimeters away from the axis. 9 is a little less, and the smaller energies are oscillating more because we would like to have as least as possible of the synchrotron radiation, so not too much bending in the higher energies. We would like to have the synchrotron radiation reduced as much as possible. So these are these very regular magnets, easy to build. They would look like this, schematically, where the permanent magnet is in the middle, the iron is on the sides. They're like quadrupoles. And they have 2 kinds, focusing and defocusing. As the particles is bent left and right, we have to have the absorption on both sides for the synchrotron radiation. We have to optimize this the best possible way. So we have a team of people who are attacking each problem. Is it synchrotron radiation? Is it the magnet? The magnet size has to be this kind. The orbits are too much on this side. Wait a minute, you have to reduce the orbit. You have to be smaller on this side if you want to have the linear function on the magnet. You have to have small offsets. You would like to have as large energy range as possible because this would raise the energy of electrons. And all these conditions are fulfilled. This is just basic dependence of the tunes, wiggling of these Betatron oscillations along the ring for one cell. So you would like to keep the tunes away from the integer and away from the half to have the orbit stable. So the previous design, we had 2,000, 3,000 magnets. Now it's 1/3. And that would be all I would say about eRHIC. Now I would like to change the subject to see what can we do in the cancer therapy. How can we apply the same method in the present cancer therapy? I have to give you some introduction. What is the cancer therapy? Why is this applicable? First of all, there was 1945 suggested by Robert Wilson that charged particles can be used for radiation treatment because they propagate and deposit almost all the energy where the Bragg peak is. But today, when you have the cancer, usually they require radiation. And the radiation treatment is done by the X-rays, almost 90% today. IMRT is the most intensity modulated radiation, is the most used method today. But the problem is right here. You can see that the X-rays shown here propagate through the body completely. They're not, no matter what you pick in this intensity modulation, the X-rays will also always affect the living cells which don't have a tumor around. While ions do different. They are located exactly where the energy of the ions is. So if you change the energy of the ions, the peak is moving. So if the tumor is, let's say, here, you have to scan it longitudinally from this point to this point by reducing the energy to the total deposition of the energy is only at the tumor. Transversely, you have to scan the beam with the additional magnets. This picture comes from the workshop organized by the National Cancer Institute, National Institute of Health, and DOE in February, where people were invited to discuss about the future carbon facility in the United States. To show you the difference between the X-rays and the proton therapy, if the tumor is presented here with a red color and treated by protons, shown on the right side, there is still some radiation around, but in this part you don't see any, while in the X-rays you do. In the other cross-section, you can see the difference too. So you don't want to affect the sensitive organs with the X-rays. In the case of carbon, it's even more pronounced localized deposition, because in proton case, there is still struggling and nuclear scattering, while in the carbon case, it's much better. So today, this is the result from end of 2012. The number of facilities with the ion treatment is rising exponentially. The number of patients treated up to date is about 100,000. These are the centers operating in the United States right now, treating patients only with protons. But in Mayo Clinic, there is one being finished. There are several being in the late advancement. There are 38, total number of 38 centers in the world. They are very expensive. The reason why they're expensive is mostly the delivery system. This is very expensive. That's the carbon top-notch facility at Heidelberg. As I said, this is the size of the man. So what happens here is, you can pay attention, this is the patient. He doesn't see all these monsters around. He's laying in this bed, and the reason why you need these gantries is you would like to deposit the energy only at the tumor, but you have to avoid the sensitive organs like spine or other sensitive organs. You don't want to hit them, you have to go around them on the different angles. So that's why gantry is a necessary burden on the therapy. So it is always required at least one for carbon, or at least one gantry to be there. So what this structure does, it oscillates 180 degrees around and allows this patient to be hit from any angle required. So in the cross-section, this is the gantry in Heidelberg. These are the dimensions. As I said, it's larger than the star detector here at BNL. So what I would like to do is, I would like to use these magnets, lay them over one by another, alternating in non-scaling FFG, and propagate the beam through this 1.2 ton gantry instead of 130 tons. So that's the saving in the weight. But as they say, for $19.99, you don't get only that. You get that all the energies pass through the same pipe without changing the magnetic field. But for $19.99, you don't get only that. You don't have to change the field at all, anywhere except at the scanning magnets. So this way, you achieve a lot of advantages. So this is the scanning magnets are here. It's also important to have all the time angle of entrance to the patient with the normal angle because of the reduce the skin radiation. These are these magnets we will be using from the BNL magnet facility, superconducting direct wound serpentine winding of Brett Parker and others designed where there is no iron. That's why it's not heavy. And it produces the field required, linear field. This was patented, belongs to the Brookhaven National Lab. So as you see in this picture, the beam is coming to the patient. This is magnified. This is from here to here is 10 centimeters. It's magnified 10 times. So you can see what happens when you scan this beam. Always comes normal to the patient. In Italy, they're already treating 2 years patients with carbon ions. And this is the magnet they built for the beam line. Again, you see the size, how large this is. So they would like to use this magnet in in an extraordinary gantry system which is eccentric, and this should be that magnet shown in this picture here, and this is their design. Not that I like this design, but this is what they want to do. So the patient, I shouldn't have stopped this. The patient is hit by different angles, depending where this position is, and it's brought by the elevator and so on and so on. But what they asked me to do is, can you do something for us, replace this big magnet with your structure? So I did that. So I used my gantry with all these scanning magnets, and I can now put through all the energies I have to put this movie somehow on. No, it's somewhere here. Okay. Problem. It worked before. Okay. So imagine that this works. I'm just... The movie is somewhere here. This one? No. Okay. So what I did here is, you can imagine this is really happening. I put all the energies through the entrance of this gantry. If it is smaller energy, they would oscillate on this side of the magnet. If it is higher energy, they would oscillate on this side of the magnet. While the scanning system, this is again magnified, this is 10 centimeters, would do the scanning transversely here. Now I'm going back to the proton gantries, which are also a very expensive part of the equipment. The problem with proton gantries today in the cancer therapy is that they always contain this large magnet because the system is designed such a way that the beam gets parallel to the patient. So this is the size of that magnet, which is 60, 70 tons. You see the man size here. So I would like to replace this big magnet with this magnet. That's the Halbach magnet, permanent magnet. It would allow me to treat the patient through the basic cell from 31 MeV to 250 MeV protons. And they would go through this is magnified 30 times, the orbits for each energy, and they would come to the patient without any problems. I can also use the same structure and make an accelerator to fit in the 6 times 10 meters, maybe from here to here, to accelerate protons with the same permanent magnets for all the energies. I can also do other scanning regular magnets with the small. And now all other applications, I don't want to waste too much time on you. I think that would be good enough for today. Thank you.
We have time for a few questions. What's the current status of the Italian project?
They are treating the status of CNAO facility is they are treating regularly the patients, but with the straight beam lines, not gantries yet, for a year and a half. The carbon.
I have a question that I'll see with a comment. So I was told by my good friend Will
Yes.
that the proton and electrons, the gamma rays, they have about the same killing effect on cancer, but the proton is more localized.
No, the electrons.
But if you use carbon, the carbon gives so much ionization density that it kills both strands of DNA. So it's much more effective. So now is my question.
Yes.
What do we have to do to get one of these carbon facilities here?
Well, this is being worked on. It was the workshop organized by the National Cancer Institute. There will be 2 facilities built very soon. One will be maybe in Walter Reed. They are very eager to build it. And the other, Walter Reed Hospital in Bethesda. The other one will be built in the Mayo Clinic. They already have the money for that. The others I don't know yet, but carbon is clearly at 6 places in Japan, in Germany, Heidelberg. Now it's finished. One in Austria is finished, being commissioned, and one in Italy has been operating a year and a half, I think, already. So it's very clear that carbon has advantages. Yes, when you mentioned the electrons don't go very deep into the body, maybe 2-3 centimeters the most. So X-rays are used for the... Right. For protons, the difference between the protons and carbon is that the minimum possible size of the protons, let's say at 20 centimeters depth, is 112 cubic millimeters, while it is 11 cubic millimeters for carbon because of the nuclear scattering and struggling of the protons in the beam, in the body.
While on this topic with carbon, Mike, the fringe benefit with the carbon is that you actually get some isotopes as it gets stopped, right? And then you get positron emitters, and you can verify your dose application basically with a PET detector that you can put around it.
Yes.
That is sort of like the thing that GSI did for a long time. I think they transferred this to hydrogen. I'm not quite sure what to say.
Yeah. Well, they were planning to use actually radioactive 13, or 11, but they did not at the end. The problem with the PET is the time scale of emitting the signal is very slow. It is very critical now item in the carbon therapy, how to get in situ, in time information of what you're doing with the treatment on time. Right now, it's very difficult to get that. They are trying very many different methods, but it's not yet widely used. It is one of the major problems in the therapy to have the information right on time during the treatment. But they do have immediately the PET scanners and the X-rays after the treatment.
How much of a problem of a fringe field be in the gantry with no iron in the magnet?
Ask Brett Parker.
Right here? He's wanting to make the aperture small and that sort of sets the scale for how rapidly it flows out. Alternating focusing. I think I still had some iron, just iron that's close in. It's highly saturated.
Brett is the collaborator for the gantry design. I am not going to design the magnet.
Well, we have wine and refreshments out in the lobby, so please thank me in thanking our speaker and then join us.